In this video, I get to introduce potential dividers. But what exactly is a potential divider? Now, a potential divider is a simple circuit, and it is meant to supply a variable potential difference, and it is normally used in audio and volume controls and various other applications. Now, in this video, I'll seek to explain the basics that are behind this the potential divider. But before we get into those basics, you're seeing a cylindrical shape. I'll call this a conductor. I've drawn here a conductor. And as you can see, this conductor has what we call, it has a cross-sectional area and it has a length. Now, from one of our previous videos, we said that all conductors have got a certain degree of resistance to flow of current. So if we are to look at this conductor, it is having a resistance to flow of current, which we shall call resistance, but this resistance is dependent on certain factors. There are actually 4 factors that affect resistance. Now, of the 4 factors that affect resistance, I would like to pull our attention to one of those factors called the length of the conductor. We explained earlier that the length of the conductor is directly proportional to the resistance of a conductor. And that is basically because the longer the conductor, the more the collisions between the electrons that are flowing through the conductor and the atoms, and so that definitely increases the resistance of the conductor. So in short, we need to remember that the resistance of this conductor is directly proportional to the length, meaning that the longer the conductor, the higher the resistance of that conductor. Now let's put this very conductor into a circuit. If we are to put this very conductor into a circuit like this, as you can see, we are having a cell right there, which is having an EMF of 12 volts, and we have connected it to this conductor. It means that as current is flowing out of this cell coming through this conductor is going to experience a potential difference across it as current flows through it. So this means that if the EMF of this cell is 12 volts, it means that the potential drop across this conductor is also 12 volts. That is on condition that the internal resistance of this cell is negligible. Now let's take a case in point. What if we disconnected this end of the conductor and we made this thing a sliding jockey? This wire, we put it around here like a sliding jockey, and we were able to slide it along this conductor. What happens? Now, of course, before we get to that, we know that as this current is flowing through, it is going to flow through that whole conductor back there. But if we are to connect it like that in such a way that now this becomes a sliding jockey, in a way that this wire slides along this conductor, it means that as current is flowing out of this cell, it will come like that. And because this portion of the wire is at that point, it means that current will just flow through just a portion of that wire. Current won't go through up to this very end. Now this part of the conductor becomes redundant. It means that as current is flowing, it will flow into the conductor and it will just continue through like that. So meaning that if I extended this right there, it means that the current coming in will only go through there like that, and it means that this portion of the conductor will become redundant. So now what does that mean? It means that as you are adjusting this jockey along this wire, it means that you are varying the effective resistance within this whole circuit. Why is that so? If the resistance of this whole conductor is 10 ohms, it means that originally current is going to experience a resistance of 10 ohms as it's flowing through back here. The effective resistance in this circuit, in other words, would be 10 ohms. But if we are to make this current not to go through this entire conductor, and we connect it in such a way that current flows and it goes through just a portion of that conductor, it means that the amount of resistance, the effective resistance in this circuit, is also going to reduce, because as current is flowing through, it's not experiencing the entire resistance of 10 ohms. Remember, when I was introducing this, we said that the resistance of a conductor is directly proportional to the length. So it means that if this is 10 centimeters and it is having 10 ohms across this entire length, it means that if we are to bring this jockey or to this wire and we connect it in the middle in such a way that here is 5 centimeters and this end is also 5 centimeters, it means that when current is flowing through this conductor, it's going to only flow through halfway the whole thing, halfway the entire conductor. And since resistance is directly proportional to the length, it simply means that if these 10 centimeters were corresponding to 10 ohms, it means that the 5 centimeters will correspond to 5 ohms. And so it will mean that if we want to find the amount of current that is flowing through the conductor, it would mean that the amount of current is only flowing through 5 ohms. It means that this 5 centimeters is only corresponding to 5 ohms of the resistance. So the effective resistance in this circuit becomes 5 ohms and this part of the conductor becomes redundant. So I would like to bring to your attention the fact that as we are varying this jockey along this wire, that the resistance of this wire will be varying also depending on the length of the entire conductor. Let's consider a conductor here. This conductor has 10 ohms and this 10 ohm conductor is connected into a circuit whose EMF is 12 volts. So this 12 volt source of EMF is releasing current in that direction and this current is going through this whole conductor and back right there. And now we are being required to find the output voltage that is just across halfway the length of the entire conductor. Now, according to the question, we are being told that the conductor is having 10 ohms. If the conductor is having 10 ohms, it means that if we are being required to find the output voltage across halfway the section of the whole conductor, it means that halfway means that it's going to be 5 ohms from here to there. This portion is 5 ohms and this remaining portion is also 5 ohms. Where are we getting that from? We're getting that from the very fact that resistance of a conductor is directly proportional to the length of the conductor. If we are to find the output voltage, we are going to first find the current that is going through the conductor. So let me call it IS, the current going through the conductor. Let me call it the source current. IS is going to be equal to V, which is 12. Divide that by R, the effective resistance in the whole circuit, and in this case it is 10 ohms, the effective resistance in the whole circuit. So it's going to be 12 over 10, and we'll find that the current flowing through this whole thing is 1.2 amperes. So now after finding the current flowing through, it means that we know the amount of current going through. It's 1.2. So now how do we find the output voltage? We are going to use still Ohm's law. Output voltage V0 is going to be the current that is going through. Remember, the amount of voltage, or the PD across this section of the wire, is going to be the same as the PD across this output. Whatever we connect here, the potential difference is the same across these two. So it means that it's going to be the current going through here, which so happens to be the source current. Multiply that by the resistance. In this case, since we are interested in the potential difference across just that section, it means that the resistance is 5 we are looking at. So it means that the output there is going to be IS, which is 1.2, multiply that by 5. And in this case, our output voltage is going to be, now if you look at this, our output voltage is 6 when we tapped halfway the wire, because it's 5 volts. Now this simply shows that actually that the total EMF in this whole circuit is 12 volts. When we tap halfway, it is simply going to be 12 divided by 2, because this is 5 volts, 5 volts. So it means that if we are saying that the total potential difference in the whole circuit, or the total EMF, is supposed to be distributed amongst the resistors in the circuit, and we are having this resistor of 5 ohms and that resistor of 5 ohms, since these two are identical, if it is 12, it means that this will take 6 volts across here, and this will also be having a potential drop or a potential difference across it of 6 volts. That's how we get 6 volts. In general terms, we shall say that if we're having current IS that is flowing out of a source of EMF. The source of EMF is what we are calling VS, and this is being connected to a conductor whose length is known, or maybe whose entire resistance is known. In this case, we are calling the resistance of this conductor, we shall call it RW. RW meaning the resistance of the wire. And we are being required to find the output voltage across a section of the whole wire. It could be halfway, it could be quarter way, or any distance across the section of the whole wire. The procedure in general terms would be that first we will have to find the current flowing through this. The current here is going to be from Ohm's law, is going to be the EMF V, which is that over the effective resistance in the whole circuit. And now in this case, the effective resistance in the whole circuit is RW, because we only have this in the whole circuit. So after finding the current, then we can go ahead and find the potential difference across the section that they are requiring. Still using V is equal to IR, we know that the output voltage at this point is going to be the current going through that portion, which so happens to be the IS that is being produced. Multiply that by the resistance across that portion, and in this case that it's going to be equal to the current IS is VS over RW, which is this. Multiply that by the resistance of this portion. Now in this case, we are saying this is halfway the whole wire. If the length is halfway, it means that if the resistance was RW, the resistance of that output portion will still be a half of the whole thing. Of course, if it is a quarter, it will be a quarter of the whole resistance, and so forth. So of course, when you multiply this, you'll find that we shall be getting an expression that the output voltage is going to be equal to the source voltage divided by 2. Looking at how we deal with this output voltage when the resistors are fixed, you see now this kind of arrangement is just the same as before, only that here we are dealing with fixed resistances. If you look at this diagram, it's like drawing this thing like this. Drawing it like this in such a way that here we are having one conductor and the whole of it's having a total resistance of 10 ohms. Because it's having a total resistance of 10 ohms, here the resistances, let's say that this continuous conductor has been split into two resistors of 5 ohms, 5 ohms. And now we are being required to find the output voltage where there is the 5 ohm resistor. Still, we are going to follow the same procedures like before. We shall first find the current flowing throughout here, IV, and which current I, let's call it the source current. IS is going to be the total potential difference, V, which is going to be V over R, that is going to be 12. Divide that by R. Now the effective resistance in this whole circuit is, we are having two resistors in series, so it's going to be 5 plus 5, which is going to be 12 over 10, and that's going to give us 1.2 amperes. And again, just like the way we did before, if we want getting there for the output voltage in this case is going to be the current that is going through this 5 ohm resistor, since the potential difference across this 5 ohm resistor is the same as the potential difference that will be across this output terminal. So it means that the output voltage across this is going to be the current going through here, which so happens to be the source current, which is 1.2. Multiply that by the resistance, which is 5. And we will be ending up with the same answer like before. So likewise, if we are to use this case whereby we are dealing with fixed resistances, in general terms, this is how it would look like. That we are having a circuit like this with an EMF, with the source of EMF, which EMF we are calling VS, the total potential difference in the whole circuit. It is having current going out of it, and this current goes through two resistors that are in series. They could be more than two. And in this case, we are being required to find the output voltage. What we do first, the output voltage, remember, the output voltage here is the same as the voltage across this resistor, since these two, whatever will be connected here, these two will be in parallel. So to get this output voltage means we are getting the voltage across this resistor R2. And it would mean that the first is to first get this IS, the current that is going through that resistor, which is going to be the potential difference divide that by the effective resistance in the whole circuit. And after getting our IS, we come out and get our V0. Our potential, V0, is going to be equal to I times R. I is the current going through this resistor, which is IS, which is this expression right there. Multiply that by R2, which is the resistor in question here. And of course, the rest is arithmetic. R2 gets right there and Vs is put out. And we end up with that expression. We can always use this expression when we are trying to find the output voltage in scenarios like this. A cell of EMF 1.5 volts is connected to a wire of length 120 centimeters and the resistance is 4 ohms. Find the potential difference across 30 centimeters of the wire. So we are only required to find potential difference across a portion of that wire. The wire is 120 centimeters. We need to find potential difference just across 30 centimeters of this whole wire. And the condition here is that if the EMF here, this cell whose EMF is 1.5, is having an negligible internal resistance. So let's draw the diagram of this and get started with the working. Now here we are having this cell. It's 1.5 volts. It is connected to a wire, and this wire, the length of this wire is 120 centimeters. So meaning that the length here is 120 centimeters. It's connected in that kind of circuit. And the question is requiring us to find the potential difference across 30 centimeters of the wire. So if the distance from here to here is 120, we are being required to just find the potential difference or the output voltage of the wire just 30 centimeters. But we know that this whole length is corresponding to, this whole thing has 4 ohms. So again, like before, to get this potential difference V, or the portion here, it means that we need to find the current going through that portion times the resistance of that end. So to get the output, V0 is going to be equal to I times R. By I, we are seeking to find the amount of current that is flowing through that portion, which we do not have yet, and the resistance of that portion, which we are still supposed to find. So let's first begin with the current. So the current that is going through this portion of the wire, let's call it IS. So meaning that current IS is going to be equal to V over R. V is 1.5. Divide that by the effective resistance in this whole circuit. The effective resistance is 4 ohms. The internal resistance here is negligible, so we only have 4 ohms. So it's 1.5 divided by 4, and 1.5 divided by 4 is going to give us 0.375 amperes. So it means that the amount of current flowing through here is 0.5 amperes. So now what about the resistance of that portion of the wire? Because we are required to find the potential difference across that portion of that wire. Remember, earlier again I said that since we do not have, remember again earlier we said that since remember earlier I said that voltage, I said that resistance is directly proportional to the length. Now the length of this whole thing is 120 centimeters, and we only need a portion of it, which is 30 centimeters. We have the resistance of the entire length, which is 4 ohms, but we do not know the resistance of that portion. So let's try and find the resistance of this portion. Since we know that R, or the resistance of the wire, is directly proportional to the length of the whole wire, we can find the corresponding resistance of that portion of the wire, so that we are able to put it right there, because it's what we are interested in. So to find the corresponding resistance of that portion of the wire, we shall say that 120 centimeters is equivalent to 4 ohms. So what about these 30 centimeters? What resistance will it be corresponding to? Let's call it X, and we find the value of X. When we cross multiply, we shall end up with X being x times that is 120. X is going to be this times that, which is 30 times 4. Divide by 120, divide by 120. And we shall end up with 30 over 120. This is actually the fraction of the wire times the total length. We shall find that this portion of the wire is just 1 ohm. So here we have the current going through that portion of the wire, which is 0.375 amperes, and we also have the resistance of that portion of the wire, which we have found to be 4 ohms. Now we can go ahead and find the output voltage of this portion of the wire, which is the current, which is this, times R, which is 1, which is 0.375 volts. And that's the answer. So now we're going to repeat this question. Part B is telling us that find the PD across the 30 centimeter of the wire if it has 1 ohm as internal resistance of the cell. So the internal resistance here is 1 ohm. That's a slight change in the question. So if I may redraw this circuit diagram, it's still going to be this. Now this time around, this cell, they are telling us it has 1 ohm internal resistance. So it's having an internal resistance here of 1 ohm. This whole thing is the cell. So again, just like before, to get the output voltage V0, for us to get the output voltage, we know we need to find the current that is going through this portion of the wire. The 30 centimeter portion of the wire, we already found out that it is 1 ohm. So this is 1 ohm, the rest of this is 3 ohms, this portion of the wire. So this is 1 ohm, yeah. And now we need to find the current times the effective resistance. Times the resistance, which is 1. Now we need to first find the current. Let's do some work here. The current, which so happens to be the source current here, is going to be equal to the potential difference V, divide that by the effective resistance in the whole circuit, which is going to be capital R. Now this so happens to be the effective, the V here, this thing is 1.5 volts, according to our question. So the EMF, or the potential difference, 1.5, divide that by the effective resistance in the whole circuit. Now in the circuit we are having this resistance, which is 4 ohms of the whole thing of this. But remember that our cell is having an internal resistance of 1 ohm. So it means we treat this internal resistance as though it is a resistor that is in series with the rest of this. So it means that our effective resistance in the whole circuit is going to be this entire 4 ohms. Add it to that 1 ohm resistor. So it's going to become 1.5. Divide that by 5. And definitely 1.5. We'll end up with 0.3 amperes. So now that we know that the amount of current going through here is 0.3 amperes, it means that the output voltage therefore is going to be 0.3 amperes. Multiply by that resistance, which is 1, and it is going to give us 0.3 volts. So that is the output voltage, or the voltage across the portion, or the PD across the 30 centimeter portion of the wire. And that answers our question. Now, of course, if you may want to use the formulas that we derived earlier in our general terms, or in the general sense, this would mean, now if I am to use this formula, in this case, it would mean that I'm going to say V0, output voltage, is going to be R2 over R1 plus R2. Now, our R2 in this case is the resistor that is across the output voltage that we want. So in this case, the resistors that is across the output voltage that we want is 1. Divide that by the effective resistance in the whole circuit. Now in this case, the effective resistance in the whole circuit is going to be this resistor here, which is 1 plus 3 plus that other resistor, which is 1. And then we multiply that by Vs, and Vs is the source voltage. And in this question, our source voltage is 1.5 times 1.5. And definitely we shall be able, when we compute that, we still get the same answer of 0.3 volts. Again, if we were to use this approach in our first question, it would still be the same approach, only that this time around, our value of R2, it's still going to be 1 over R1 plus R2. Now in our first instance, remember, this 1 ohm was not included. It was not part of the deal. So it means that in our calculation, in the first instance, this 1 would be excluded, and would continue doing our question like before, and would still get our answer.